Hello, everybody. Today we're going to be looking at some more techniques for evaluating integrals, especially when we have integrals and we've tried every possible analytic method that we know of for evaluating an integral, and we still can't figure it out. Then the last two things that we can try are using a table of integrals. There's actually a table of integrals in your book called the brief table of integrals, and I'll show you how to get there from if you're using the Pearson. If you are using the Pearson online textbook, you can click on e-text. And there is a table of integrals on the menu here. At the very end, we have a brief table of integrals. So that's provided in your textbook. Just about every textbook has a table of integrals. They're not all exactly the same. They're not probably numbered the same, but you'll see this goes on for several pages, and they did call it a brief table of integrals, but if you scroll through or turn the pages in your book, and so this is actually the last page. So their brief table of integrals has 156 different integral formulas in it. And the reason why it's called a brief table is because there are actually entire books. You can buy a book, or probably more available online now, but back in the day when I was in college at UC Davis, all the math majors, we carried around this book that was about 2 inches thick, and it was just a table of integrals. And engineering majors needed those as well because we didn't have graphing calculators, we didn't have online integration tools, so we had to rely on these big, thick books that were just full of integral formulas to evaluate integrals when we couldn't do them by hand. Okay, so we'll go back to some problems here, and we'll get some practice using this table of integrals. And the table of integrals is kind of organized by format. As you can see here, we have a bunch of integrals on this page they look like they're all related to hyperbolic trig functions. And you'll see they're organized together. These ones all have integrals of the form a constant plus a constant times a trig function. So b plus c sine, this is b plus c cosine, and so on. Trig functions alone, trig functions in the numerator. We have a bunch of different varieties. So you just kind of look by category until you find an integral similar to the one that you're trying to evaluate. And so this one, if I expand this would be 1 over 5x squared plus 2x dx. And I can look in the table of integrals for one that looks like that, or possibly in the original format. So if we look through, if you go to formula number 26, let's see if I can pull that one up here. Formula number 26 looks like our original problem, so I didn't need to distribute, it looks like. So formula number 26 down here shows that if we have x times a linear expression ax plus b, we can evaluate it this way. And so we'll have, using that formula, we'll have a is equal to 5 and b is equal to 2. Okay, and so we didn't need this. And so according to that formula, the antiderivative is going to be 1 over b, so that's 1 over 2 natural log of the absolute value of x over ax plus b. So that's 5x plus 2 plus c. So that was using formula number 26 from the brief table of integrals in the back of your book. Okay, go ahead and take a look at problem B. See if you can find an integral formula that'll match that. So we're probably looking for something of the form 1 over a plus b sine of cx, something like that. See if you can find one that'll work, and if not, one that's close enough that we can reconfigure this. Pause your video, try it out, and then press play when you're all done. All right, so problem number B looks a lot like formula 77 and 78 here. We have a constant plus a constant times sine of a constant times x. And so both 77 and 78 look, they look actually the same. What's different is at the end, it says one of them if b squared is greater than c squared or if b squared is less than c squared. And so I'm going to paste those formulas here so that we can look at them. And so from this format, we would say b equals 8, c equals 3, and a equals 5. And so b squared is 64, c squared is 9. So our b squared is bigger than c squared, so we're going to use formula number 77. Okay, and so according to this integral then would equal negative 1 over a is, a is 5. I'm sorry, so it's negative 2, not negative 1. So negative 2 over 5 square root 64 minus 9 inverse tangent of square root of 8 minus 3 over 8 plus 3 tangent of pi over 4 minus 5x over 2 plus, and then this can be simplified as negative 2 over 5 root 55 inverse tangent root 5 root 5 over 11 tangent of pi over 4 minus 5 pi or 5x over 2 plus c. And that's it. Okay, so now if you focus your attention on these formulas in the back of your book, 67, 68, 75, 76, 87, and 88, those are all referred to as reduction formulas. Let's take a look at those. Okay, so 67 and 68. Notice that we start with a sign with a power of n, and it gives us an answer with a sign with the power of n minus 1, and then it gives us also part of that answer is an integral with a power of n minus 2. So every time you use this formula, you still get another integral to evaluate, but it's decreased by a power of 2. So these are called reduction formulas because the power of n is reduced by 2 every time you use this formula. And so you continue using it until you eventually have a small enough power that you can evaluate it. by traditional methods. Same thing with 68, except it's cosine. It starts with a power of n, and then you end up with a new integral with the power of n minus 2. So the power is reduced by 2 every time you apply this formula. And then similarly for 75, this one we have sine to the n and cosine to the m. And so this reduces it to reduces the power of sine by 2 every time you apply it. Same with 76, except it reduces the power of cosine by 2 every time you apply it. And then the other two were 87 and 88, and those are when you have a power of x times sine, so x to the n times sine, you can reduce it to x to a power of n minus 1 times cosine. So it reduces the power of n by 1 every time you apply it. So that looks very similar to what we did with integration by parts. So you would suspect that probably formulas 87 and 88 came from several applications of integration by parts over and over again. Okay, so those 6 formulas are called reduction formulas. So we're going to practice using those next. And so for example 2, we start with sine to the 7th power. And so we're going to use that first formula, number 67. So here's formula 67. That's going to allow us to reduce let me get that out of there. Put it over here. Okay, there we go. All right, so now using formula 67, it's going to reduce the power of sine, which starts at n equals 7. It's going to reduce it by 2 each time we apply it. So if we can eventually get it down to sine squared, then we'll be able to evaluate the integral. And so we start with n equals 7, a equals 3. And so applying this once, we end up with negative sine to the 5th of 3x cosine 3x over 7 times 3 plus 6/7 integral of sine to the 5th power of 3x dx. So the power has been reduced by 2, so now we can apply it again, this time using n equals 5 and a equals 3. And so then we'll simplify as we go. This first one becomes negative sine to the 5th, 3x cosine 3x over 21. And then this is going to be 6/7. All the stuff inside the integral now we're going to replace with the reduction formula. So now it's going to be negative sine to the 4th power of 3x cosine 3x over 5 times 3 plus 4/5 times the new integral is going to be sine to the 3rd power of 3x dx. Okay, and now that is going to be, we can simplify this using n equals 3, a equals 3. And so as you can see, we just keep applying the same formula over and over until we have an integral that we can evaluate by hand. And so now our next one is negative sine to the 5th x of 3x cosine 3x over 21 plus 6/7 negative sine to the 4th of 3x cosine 3x over 15 plus 4/5. And now we're going to use our reduction formula again with n equals 3, a equals 3, and we get sine squared 3x cosine 3x over 3 times 3 plus 2/3. New integral is now sine 3x dx. And that is an integral that we can evaluate by hand. And so finally now we have an answer. So the antiderivative of sine is negative cosine 3x over 3. And now we are all done, plus c. So that can be simplified further, but as I've expressed in the past, there's not really any advantage to simplifying that. So that is our correct and final answer. So go ahead now and see if you can find a reduction formula that will help with B. And pause your video. Try getting all the way to a final answer with this one, and then press play when you're ready to see the solution. So looking at the table, we see formulas 99 and 100 are the reduction formulas for secant and cosecant. So you can add those to your list of the ones that we had earlier. And so using formula number 99 with n equals 6 and a equals 5, you can see all the steps here. So you can check the final answer at the end, see if yours agrees with that. And if not, then go back through and look step by step and see where you might have done something a little bit differently. So you're welcome to pause your video and look at that for as long as you need to. Our next topic is on using computer algebra systems, which is abbreviated CAS. Some of you may have seen calculators that you had in high school, or your school might have had some in the classrooms, or some of your classmates might have had calculators that said CAS on them, like the TI Inspire CAS. What CAS stands for is Computer Algebra System. So a lot of those expensive calculators like the TI Inspires have a CAS system built in where they can do a lot of calculus on them. There are also software packages like MATLAB and Maple and Mathematica that you actually have to pay for, and you get very sophisticated math systems that can solve many different differential equations, integrals, derivatives, you name it. These programs are built to do those for advanced mathematics. The one we're going to look at today is free online, and that's why we use it, and it's also very easy to use compared to MATLAB and Maple and Mathematica. Those are a little bit more sophisticated, and it takes a little bit of syntax knowledge, coding, and so on to be able to use those. But Wolfram Alpha is very easy to use. And so I've got the link for Wolfram Alpha here. You can either type that in or copy and paste possibly. And so we're going to use that to solve a problem like this. You'll notice this problem, you're not going to find anything in the integral tables that looks like that. And so that would be a pretty tough integral to evaluate. And yet using Wolfram Alpha, it's not too tough. And so here's how that's going to work. You'll want to probably write that down, and then we're going to go to Wolfram Alpha, and you should as well open up a new tab and go to this Wolfram Alpha link. Okay, and here you can type in pretty much anything you want as far as integrals. You can just type freely in English and say integrate. Let's say something like x squared plus 5 from x equals 2 to x equals 7. So you can just type freely in, using the English language, and it'll interpret what you said. And so there it is. There's an integral from 2 to 7 of x squared plus 5. And it gives me an answer and gives me some graphs to go along with it, and so on. So very useful. So for the problem that we were just looking at, we wanted to integrate cosine of 3x. I'll put, cosine of 3x divided by, parentheses, sine of 3x sine of 3x plus 1 squared. Then we have to give it endpoints. This one actually doesn't have endpoints, so we'll just leave it like that. So we want to integrate that expression. I'll close the parentheses for the bottom and then press enter. And it thinks for a moment. And then finally gives us this entire answer. Basically everything from the equal sign from this left parenthesis here all the way to the constant at the end. That is our answer. So not one that you probably would have been able to do by hand. All right, so now go ahead and try using Wolfram alpha on problem B. See if you can find the antiderivative of that expression using Wolfram alpha. Okay, so typing this into Wolfram alpha, a couple things that might be helpful is that in Wolfram alpha, if you just type log, that is the natural log in Wolfram alpha code. So you can type in ln, but it'll change it to log. If you want to do a common log, you actually have to type in log base 10. And so instead of writing ln, you just write log x. And to do a square root, I just type sqrt. There might be other ways to do that, but typing in sqrt will always give you a radical. And so when I put that into Wolfram alpha, that looked like this. So integrate log x divided by x times the square root of 4 log x minus 1, and then the two parentheses at the end. And so it wrote the integral correctly. Notice here there's a note. It says assuming log is the natural log. And so this is the answer it gives us, 1/12 2 natural log x plus 1 square root of 4 natural log x minus 1. So you can compare that to what you typed in and what you might have gotten as your answer. And that is it for the notes. And here are some problems that you can try out. And even though you don't have the answers to the even numbered problems, now you can use CAS to check your answers. So you could do some problems using maybe the integral table, the brief table of integrals in the back of the book. And then you could also check the answer using Wolfram alpha as your CAS. All right, have a good day, everybody.